Okay, so higher order differentiation. Basically, we've differentiated, we've worked out dy by dx, or we've worked out f dash of x. Well, you could carry on. You could differentiate again. So if I was to differentiate dy by dx with respect to x again, the notation that we have for that is d squared y, and dx squared on the bottom. So that's the notation for when I differentiate dy by dx. An easier notation is if I differentiate f dash of x, we get f double dash of x. Therefore, to differentiate this, we already know we get 3x squared, take 2x plus 2. And what I'm saying is that we can now differentiate that again using the notation that I've just said. And differentiation of that would be 6x. Differentiation of that would be 2. Differentiation of that, nothing. Second differentiation, d2y by dx squared. And likewise, if I first of all rewrite that one because of the second term, 1 over x we know is x to the power minus 1. And then the differentiation of that is 2x for the x squared. Bring down the power, so positive 1 x to the power of minus 2. That can be rewritten as 2x and that as 1 over x squared. However, for the purpose of the second derivative, I use this. Differentiation of 2x is 2. Differentiation of the 1 lot of x to the power minus 2 is minus 2 x to the power of minus 3, which again can be rewritten as 2 take 2 over x cubed. So again, if I rewrite square root of x as x to the half, that as 4x to the power minus 2, we're in a position to work out the first derivative, f dash of x. Bring down the power, take 1 off the power, bring down the power, take 1 off the power. That can be rewritten, and we've seen that a couple of times. So we have that, and that can be rewritten as that. However, I'll go back to this for the second derivative. Bring down the power, so minus a half times a half, minus a quarter. Take 1 off the power, we get minus 1.5. Bring down the power, so 24. Take 1 off the power, minus 4. Now that one can be rewritten. We know it's minus 1 over 4, and we have the x on the bottom. Now we have x to the 1.5, x to the 1 and a half, x to the 1, x to the half. And this one is quite simply 24 over x to the 4. So let's have a look at this from a different angle now. Here, I've already given you the differentiation, the second derivative. Well, I can work backwards and find what the differentiation was, because that had to have come from x squared, because x squared differentiates to 2x. That had to have come from minus 1x, because minus 1x differentiates to minus 1. However, there must have been a constant on there, possibly, because a constant would have differentiated to nothing, so I need to put that in place in the event that there was one. However, I have been told that the differentiation was equal to 0 when x was equal to 0. So if I put nothing in there, the whole thing has to be nothing, so I know in this case that there was no constant there. Repeating myself, I can initially think that that must have come from x cubed. But when I differentiate that, yes, I get the x squared, but I would have ended up with a 3 at the front, and I don't want a 3 at the front. So therefore I must have had a third at the front to counteract that. What I'm saying is, bring that 3 down, 3 times a third is 1, take 1 off the power, x squared. Likewise, minus, that must have come from x squared, but exactly the same. Differentiate that, I get 2x. Therefore, I need a half at the front. And once again, I must consider the fact that there could have been a constant, because the differentiation of constant is nothing. Now here we're told that the value of y is 2 when x is nothing. So nothing, nothing, the whole thing's got to equal 2, so that constant there must have been equal to 2.